Good morning everyone. I am Nikita Mishra from Department of Chemistry, Gujarat University. Welcome you all in the online refresher course in chemistry hosted by Department of Chemistry, Gujarat University, Ahmedabad. On behalf of Dr. Jagdish Joshi, Professor, Director, UGC HRDC, Gujarat University, and Dr. Dilip Vasawa, Assistant Professor, Refresher Course Coordinator, HRDC, Department of Chemistry, Gujarat University.
Welcome you all in the session of Dr. Charulata Dubey, Assistant Professor, School of Nanosciences, Central University of Gujarat, Gandhinagar, India. In her academics, she has completed graduation from Azamgarh and post-graduation from Gorakhpur. She has completed her MTech and postdoc and doctorate degree from Indian Institute of Technology, New Delhi. In her research work, the thrust area includes development of advanced material for water purification, stimulation of radiation damage in nuclear fission and fusion materials by employing surrogate method of ion radiation, characterization of ion beam induced radiation damage, nanotechnology, microprocessing of materials. She is also an independent international collaborator with radiation damage study in iron phosphate glasses and zirconolite glass ceramics, Germany, stimulation of alpha damage of iron phosphate glasses, CEA, France, stimulation of damage caused by decay of nuclear waste glasses, IUAC, Delhi. In her research contribution, she has 21 research publications and 7 conference proceedings in various national and international conferences. Additionally, she has 6 technical reports, 3 book chapters and 2 ongoing projects. She is also a part of invited talks. She has given more than 20 invited talks in various workshops, webinars, seminars and conferences. She has presented and attended a conferences and workshops more than 30. She was involved in teaching of masters and PhD students. She also took several lectures of material selection and properties for different applications. Visiting faculty of Nanotechnology Education and Research Center, NERC, India. Guest lecture in Delhi University. Guest lecture at Central University, Gandhinagar. Provided teaching assistant for BTech physics laboratory classes. In her achievements, she was awarded 100% financial international travel support from DST India to attend conference at USA. Represented IIT Delhi in Japan as a part of JENES 2008. Best Poster Award in Open House Competition, IIT Delhi. Highest CGPA Award for 2005 PG batch in IIT Delhi. First runner-up in MTech at Department of Physics, IIT Delhi. National Eligibility Test conducted by CSIR Government of India in 2004. Cleared Joint Entrance Screening Test by DAE Government of India in 2003. Graduate Aptitude Test in Engineering GATE conducted by MHRD Government of India in 2003. Apart from this, she has computer skills and programming languages experience, COBOL, Pascal, C, C++ and various softwares. She has editorial experience as a reviewer for Ceramic International, Journal of Alloys and Compounds, Journal of Fusion Science and Technology, Journal of Radio Analytical and Nuclear Chemistry. She has professional membership as a lifetime member of Society for Material Chemistry, lifetime member of Powder Metallurgy Association of India, lifetime member of Ion Beam Society of India, lifetime member of Plasma Science Society of India. She is also expertise in various instrument handling like scanning tunneling electron microscope SAM-TEM, vibrating sample magnetometer at low and high temperature, FTIR, UV visible and Raman spectroscopy, XRD machine, and LCR meter. She has completed 2 projects. She has contributed as a resource person in more than 10 courses. In her research supervision, 2 MPhil and 2 PhD has completed and 3 PhD are ongoing. Thank you.
Hello everyone, myself Dr. Chawla Zarure. I am employed as an assistant professor in School of Nanosciences at Central University of Gujarat. Today I will be talking about the electron microscopic techniques for the characterization of materials. Materials can be at different scale like microscale, nanoscale, and sometimes it is not possible for us to see with bare eyes. So we need some instrument which can be magnify the object so that we can see. The utility of the magnifier kind of microscope is for the microstructure and surface morphological study as well as for 3D investigation. Sometimes this electron microscopic technique can be used for the composition analysis as well. So let's start. So what was the need to invent this microscope? So just now I mentioned that small object cannot be seen with bare eyes. So we need some help of instrument. So here are some example of magnifying instrument like magnifying glass. So magnifying glass is a convex lens. It is generally kind of framed in a handle. You can see over here. So in our childhood, we used this kind of magnifying glass to concentrate sun radiation, and as a result, a kind of hot spot got generated, and eventually there was kind of fire. It was fun activity at the childhood. On the right hand side, you can see optical microscope. This is the image of typical microscope we have seen in our 10th or 12th class physics or chemistry lab, maybe 12th class physics and chemistry lab for the investigation of different kind of investigation. Let's so optical microscopy. In optical microscopy, the probe is light. So this is earlier nearly 400. This is 400-year-old technique. So generally, scientists and engineers used to see the microstructure of material. So very old technique in that sense. Now this is very important how to select any microscopic technique. So the very first thing we have to be very familiar with the dimension of our object. So depending upon the dimension of object, we have to select our technique. Suppose if you have some dimension in kind of micrometer, so even our optical microscope is well enough. But suppose your material is in some nanometer scale, then we have to go for the electron microscope. So in general, even optical microscope or electron microscope, resolution is function of wavelength. So this is a typical electromagnetic spectrum. Here you can see the ranges of different objects. As you can see over here, that this is the size. This is for the reference. So human eye can see up to this point. This is around 150 micron. This is a dia of human hair. So we can see up to here without aid of any instrument. But beyond that, we need light microscope, which can go up to 400, 500 nanometers. But beyond that, this light microscope can't assist us, so we have to go for the electron microscope. Why electron microscope? The probe which electron microscope use, that is electron. Electron is having shorter wavelength, means shorter than the light. Generally visible light is having kind of wavelength that is from 400 to 700 nanometer. However, electron microscope is having wavelength shorter than even 400 nanometer. So this is very important to select our instrument very carefully. So one should be very much clear about what we want to see in our object and what is the range. Can it be seen with the light microscope? Then well enough. If it can't be seen with the light microscope, then we can go for electron microscope. If it is possible with the scanning electron, if sample preparation for the scanning electron microscope is very easy. If it is not possible with this SCM machine, then we go for the transmission electron microscope. Sample preparation for the transmission electron microscope is big tough. So here is comparison between optical and electron microscope. You can see that optical microscope and electron microscope, that in transmission electron microscope, is very much similar. Optical system is very much similar. So as in the optical microscope, even transmission electron microscope is having a condenser lens, then objective lens followed by projection lens. However, for the SCM machine, optical system is bit different. We will discuss it later. So in this sense, optical and electron microscope are very much similar, especially optical microscope and transmission electron microscope. So let's have a look at the optical and electron microscope. What is the difference between the magnification and resolution? What is the magnification? Magnification is defined as the ratio between the image size to the object size, and it can be changed by the distance between object and the final lens. We will see how what does it mean. So magnification with the electron microscope is usually 1,000 times better than the optical microscope. Resolution, how about the resolution? Resolution is defined the point at which two or more objects can be distinguished as a separate object. Suppose these are two objects. So how well these two objects are separated together? That will be decided by the resolution limit of the instrument. So for electron microscope like transmission electron microscope, resolution limit is 0.5 nanometer, which is 1,000 times better than optical microscope. So here again the definition of magnification. This is the ratio between the image size and the object size. As we can see, if we suppose we insert some instrument here, let's say magnifying glass. So just by changing the distance between the object and the final lens, we can change the magnification of the image. Now resolution, as just now I mentioned, this is the defined at the distance at which two images can be well resolved. So what is the main difference between the optical microscope and electron microscope? So in optical microscope, we use light as a probe, and it is having a kind of wavelength. It uses visible light of wavelength 300 to 700 nanometer roughly. But in electron microscope, as we all know, the electron is having dual nature. That every particle is having wave nature as well as wave is having particle nature. Here we are assuming that electron is a particle, so it is having wave nature as well. So wave nature of electron is represented by, this was first given by the de Broglie. So with every particle there is a wave associated with the particle, it is known as a de Broglie wave. So wavelength of de Broglie wave is given by lambda is equal to h by mv. We can see here, if we increase the velocity of the electron, the wavelength associated with the electron will go down and down. With the optical microscope, we can't go beyond 380 nanometer. But with electron, we can go even beyond less than 300 nanometer, just by increasing the velocity of the light. That's why we are switching from the light to wave to the particle. Particle we can control by changing the acceleration voltage with increasing the velocity of the particle. This is the main advantage. This is the kind of motivation for changing from the light to electron. Now image resolution in optical microscope. This is very familiar formula we have done in our 10th or 12th class physics or chemistry. Resolution, again, this refers to minimum distance between 2 points at which they can be distinguished. The typical formula is R is equal to 0.61 lambda divided by mu sin alpha. So for air, mu is equal to 1, and if we take visible light, typical visible light 400 nanometer. So best resolution with optical microscope is 0.42 micron. However, suppose we have some features in our sample which is less than 0.2 micron, it won't be well resolved in optical microscope. Then what is the need? We have to bring down this lambda value. How we can bring it down? So simply just now I mentioned we can bring down the lambda value. We can shift from the wave nature to light nature, from light to electron. So this is the motivation for shifting from the light to electron. So this is again de Broglie wavelength associated with the particle like electron, or any particle, any moving particle with like electron. So if we increase acceleration voltage, this is the kind of acceleration voltage in the electron column. We will see just now what does mean by electron column. So if we increase voltage, as you can see, if we are increasing voltage, so accordingly wavelength associated with the electron is decreasing. Here it is 0.004 nanometer. Again at 200 you can see this is just half, 0.002 nanometer. So if we keep on increasing the acceleration voltage, the wavelength associated with the electron will go down. If the wavelength will go down, so what will happen? So resolution of the instrument will go down. Just now we have seen that resolution is directly proportional to wavelength of the probe. So let's again come to the electron microscope. This is again de Broglie wavelength associated with the electron. This is your typical of the electron gun. This is source of the electron. They are being accelerated through acceleration column. So suppose if you are applying 80 kV, so wavelength corresponding to 80 kV for the electron, that is lambda, that is the de Broglie wavelength, will be 0.004 nanometer. If we increase voltage from 80 to 100 nanometer, it will go down to 0.003 nanometer. So as a result, resolution of the instrument is improving. If we keep on increasing the voltage, resolution of the instrument is improving. So typical acceleration voltage is generally 60 to 100 kV in SCM machine. So wavelength is just by controlling the wavelength or acceleration voltage, we can improve upon the resolution of the system. So now here is some milestone in the history of electron microscope. We all know that electron was discovered by J.J. Thomson in 1897. Again I mentioned the de Broglie concept was given by de Broglie in 1924. It was concept that every particle is having wave nature as well as wave is having particle nature. That is known as a particle wave duality. So again there is a different kind of progress in the electron microscope. Finally, HRTM came into picture in 1986, 1970, and 1986 Ruska got the Nobel Prize for the same. Let's come to the scanning electron microscope. Basically, SCM is formed by focused electron beam that scans over the surface area of the specimen. So, SCM machine is having very good magnification, starting from 20 times to 100,000 times magnification. The important thing is that it can give us the compositional analysis as well as. SCM is having resolution around 1 to 20 nanometers. However, in the TM, it can go up to 0.5 nanometer as well. We will come to the TM later on. So let's start with the instrumentation. This is the electron source, and then there is a set of optical path. Electron beam is controlled through the electromagnetic lenses. So this is condenser lens that it can go again after condenser lens it goes to the scanning coil. After scanning coil, what does the scanning coil does? It deflects the electron beam. Then it goes to objective lens. Here interacts with the sample. Then different kind of signals comes out of the sample that is being analyzed in SCM machine. So we have mainly three systems. First one is electron optical system, then sample stage over here, then number of detectors over here, and then image display unit. This is the instrumentation part of the SCM machine. Let's come to the signal detection. What kind of signals come from here? So as just now mentioned, whenever incident electron will be here, so there will be some there will be different kind of interaction. So the most important is secondary electron. What does mean by secondary electron? There are electron may scatter elastically as well as inelastically. If it is scattered elastically, means without any loss of the energy, so it is known as a back scattered electron. If it is scattered inelastically, means there is loss of the energy of the electron, they are known as a secondary electron. So generally secondary electrons are used for the topographical contrast and back scattered electron for compositional contrast. There are other signal also like X-ray. Generally this is used for the compositional analysis of the sample. So this is we call it EDS or WDS analysis, energy or wavelength dispersive analysis of X-rays. So these X-rays are analyzed and this gives information about the composition of the sample. So basically elastic scattering, this is whatever we get from the elastic scattering, they are known as a back scattered electron. They are the incident electron, the same incident electron, they are scattered by atom in the specimen. Inelastic scattering, however, they are scattered ejected from the atom. Suppose this is atom, electron is coming. So if it is scattered from the atom itself, then it is back scattered electron. If some electron is ejected from the atom, that is the secondary electron. So this is the basic difference between secondary electron and back scattered electron. Back scattered electron are scattered by atoms in the specimen, but the secondary electrons are ejected from atom in the specimen. This is very important to note because these are two very important signals in SCM machine. Secondary electrons, main role of the secondary electron is for the topographical analysis and back scattered electron for compositional contrast. Let's move ahead. Now let's come to the electron specimen interaction. Once electron is inside the sample, so it is there to lose their energy. Okay, so there can be different kind of interaction, elastic and inelastic. In elastic interaction, it may scatter from the atom and it will produce back scattered electron. So back scattered electron, you can see that top 300 nanometer here, they will give compositional contrast, and top, you can see top 50 nanometer, it is you this is the volume from where the secondary electron comes, because it is coming from the atom itself, not scattering from the atom, it is coming from inside the atom. So that is why it is used for the topographical contrast. Or and then there are other signals like X-ray, just now I mentioned. So there are different kind of interaction between a specimen and incident electron beam. One more thing, that is the electron probe diameter. We will come across this. So this is the trajectory of electron beam once it is inside the, this is simulated through Monte Carlo simulation. This is the ET detector. So this is if you see, there are different kind of electron beam. This is the secondary electron, B is for back scattered electron. So this is very commonly used detector. This is known as the ET detector. Here the SC travel with large diffraction. You can see here it is travel with large diffraction towards the detector. However, this back scattered, you can see this is directly traveling towards the detector. Again, there is a Faraday cage. If suppose if it is in front of the detector itself, here you can see, if it is negatively charged, so what will happen? Suppose, so the secondary electron ejected, they have very less energy, just few eV, so they will be stopped. However, back scattered electron will reach the detector. So in this way, just by changing the potential kind of this value charging, we can select the electron, whether we are kind of, whether we can select secondary as well as back scattered electron just by changing the kind of potential applied to the Faraday cage. So this is one way to select the secondary electron or back scattered electron. Now let's come to the contrast formation. This is again very important to understand the SCM image. So there are two kind of contrast, topographical and compositional contrast. Let's understand topographical contrast. What is a contrast? Basically, you can see this picture. Why? Because background is white and this font size is in black. Then why you can see? Suppose if I have selected it is in yellow color, very light yellow or light sky blue, so you won't be able to see. Or if you can see very with very hard, it was very tough to see this light. That's why generally it is suggested to go for black and white. Why contrast is good? So similarly for the SCM also, what is going to create contrast? That is number of electron. From some area, if number of electron is going to come in large number, so that will be brighter. From some area, if it is number of electron is coming in a less amount, that is going to be kind of dark. So that is going to create in contrast in your SCM image. So basically topographical image refers to variation in signal level. What is variation? What is signal here? That is number of electrons which is coming from the different area in your specimen. That will give about the ventricle as well as compositional information about your sample. So for topographical contrast, it is the primary source of contrast in SCM image. How we can go for the topographical contrast? That is from the secondary electron, that is inelastically scattered. Again, this kind of contrast is constructed from two effects. that is a trajectory effect, then electron number effect. Let's move to the trajectory effect. As the name suggests, the trajectory effect means there is a this contrast is or due to the path difference in the trajectory. So let's focus on the variation. Suppose this is your sample. This is some feature in your sample. Okay, it arises some variation in sample, and it is your detector over. Okay, suppose some electron is being ejected from this sample, this surface as well as this surface. Whatever electron is ejected from this surface, it is going this direction, and if it is ejected from this surface, it is going in this direction. Similarly, this will go this direction. But suppose some surface from where this electron is going directly straight to detector, so this surface will look brighter. So this area will be brighter. However, the area which is not facing towards the detector, they will look dull. So this due to the trajectory work, there will be topographical contrast. So the electron emitted from the surface which is not facing the detector will reach the detector with difficulty, and the area which is facing the detector will reach the detector very easily. And this trajectory will create a contrast in the number of electrons reaching the detector. That's why it is known as a trajectory effect, which is creating the contrast. So this is again, you can see the area which we are facing the detector, they are looking brighter. If this area is brighter, it means your detector will be somewhere here. That's why your area is brighter. Okay, if detected here, that's why this space you can see it is dull. Similarly, your detector is somewhere here, that's why this area is brighter. Number of electrons reaching the detector is high in this area. Similarly, over here, over here. However, the opposite faces which you can see, number of electrons reaching the detector is not enough to create. So the area from which, like this area, it is very hard for the secondary electron to reach the detector. That's why this area is looking dark in the image. However, the faces which is directly facing to the detector, they are looking brighter like this. So this contrasts to the trajectory effect. Second one is the electron number effect. Again, very interesting. Suppose you have some topography in your sample like this. This is a schematic of some topography. So when the electron probe hit the sample at an angle, let's say assume this angle, let's assume you have some this kind of feature in the sample. So what will happen, this is your some curvature in your sample. So and then your sample is having some flat area also as well as some curvature. So what will happen, if you see from flat area, they are having less number of electron coming out from the surface. But if you see the trajectory one, large number of secondary electron are coming from the curved surface. So if your sample is hit a surface, suppose at an angle, more number of electron will escape from the specimen than flat sample. So it will reflect in your topographical contrast. So whenever there is a sample which is hitting electron at some angle, so large number of electron will escape from the curved surfaces than flat surfaces. This will create contrast in number of electron reaching the detector. So this will lead to that certain area in the specimen, such as curvature, they will look brighter, and however the flat samples will look darker in the image. Let's take an example. So this is example of electron number effect. So this is your grain boundary. Can you see this bright line? So here the electrons are seen are kind of escaping from the this point. So that's why they are brighter. However, this is flat surface. So less number of electron reaching to the detector. So we can see grain boundary very nicely. This is flat surface, less number of electron reaching the detector. So it is moderate. However, grain boundaries are quite bright in the nature. Here we can see some inclusion, again something, that's why it can be used for the 3D analysis also due to electron number effect. Let's come to the compositional effect. Till now the trajectory effect, electron number effect was it due to the secondary electron. Now we are coming to the backscattered electron. What was the secondary electron? Secondary electron was inelastically scattered electron which was coming out of the atom. It was not scattered from the atom. Now we are coming to the backscattered electron. Backscattered electrons are electrons which are scattered from the atom inside the sample. They are going to create compositional contrast. So this is again related to the composition. As I mentioned in the very first, the backscattered electrons are electrons which are scattered from atom inside the sample. So if it is being scattered from the sample, suppose we have two things. One is having copper, second one is tungsten. Tungsten is having high number of electron, so scattering of electron from the tungsten will be higher than copper. So the area where tungsten is there, so it will look brighter than copper one. So that due to that difference in the Z value, that is atomic number value, it will be seen in the image also. So basically composition contrast is attributed to the backscattered electron. Whenever we will collect compositional contrast, how we can collect backscattered electron? Just by changing the voltage to the Faraday cage, to the ET detector. So difference in the number of backscattered electron collected by the detector will appear in gray scale, either in black and white. Suppose you have just now mentioned copper and tungsten. Suppose if it is tungsten, it will look brighter. If it is copper, so it will look not that bright. So just by the brighter scale, we can compare that these are two atoms there. So higher atomic number will appear bright. So this is how we can distinguish what kind of elements are. There is one more way we will come across, that is the X-ray analysis. So this is a compositional contrast. Same image. This is constituted from the secondary electron. This is the backscattered electron. Here you can see the bright element is, let's say, copper, and the less bright, that is a gray scale, that is due to the copper. So immediately you can make it out. There is some difference in the composition of the material. Let's move our resolution. Resolution is again very important parameter for the electron microscope. How we can control the resolution? Because of resolution only we have shifted from the optical to electron microscope. The in optical microscope, resolution was decided by the wavelength of in visible laser. The minimum wavelength possible is 400 nanometer. We can't go beyond that. However, with electron, just by this dual nature, we can de Broglie wavelength, we can apply X-radiation voltage, we can X-rate electron, so the wavelength associated with the electron can be shorter and shorter. So it can see shorter features and it can resolve shorter features. So here is expression for the probe diameter. So this is the area at which the electron is hitting the sample. So this is the expression for the probe diameter. This is the probe current which is flowing, the amount of electron which is going inside the sample. Again, beta is the beam brightness. This is generally controlled by the X-radiation voltage as well as the electron source. So generally there is different kind of gun. Like in typical older SCM machine, there is tungsten thermionic gun. Nowadays there is field emission gun, and this field emission gun we call it FESCM, field emission SCM. So generally, and there is in conventional SCM there is a tungsten in older days. Nowadays LAB6 is there. That filament, that electron gun is source is of two kind, that is tungsten, that is again thermionic emission. LAB6 also thermionic emission. However, LAB6 is 100 times better than the thermionic tungsten one. But field emission gun is 1000 times better than thermionic gun, that is tungsten. Nowadays, generally we go for field emission only. Again, one more important parameter is alpha f, that is the convergence angle. What is a convergence angle? That is a kind of determined by the final aperture and the working distance. This is very important. Working distance and final aperture. So in order to improve, go for the better resolution, we have to control our probe diameter. So to get high resolution, we have to minimize probe size. How we can minimize probe size? Just by increasing brightness and alpha f. That is the how we can kind of maximize this beta, just by shifting from the thermionic gun or LAV6 to field emission. That's why in field emission we can go for better resolution. Nowadays everyone goes for the field emission. This is the reason, that's why we opt for the field emission, because here the size of the probe is smaller. This size is smaller, that's why we get better resolution. This size is smaller, that's why we get better resolution. And what is the other way? The one is beta, that is why we are going from the conventional SEM to FESEM. Second one is alpha F, that is how we can kind of increase this by increasing the working distance. We have to increase this, that then only it will go high and high. So these two parameters can be controlled by the adjustment of this sample stage or by adjustment of the electron source from going from the conventional SEM to FESEM. Now specimen preparation. Some precaution needs to be taken care for the SEM preparation. We are going for the topographical information. The moment I am saying topographical information, it means I am talking about the secondary electron, that is the inelastic electron. So for this topographical, minimal sample preparation is required. First, you need to select your sample size so that it can be mounted on your sample stage. In the machine, you have to check what is the size of the sample stage in your machine. Okay. Now you have to remove sample contamination. Number of contamination. Even if you touch by hand, then also it will get contaminated. So you have to clean it very nicely. To remove all kind of contamination by some organic solvent, maybe acetone or methanol. Dip your sample in some solvent, organic solvent, and then put it in ultrasonic cleaner, maybe 10 or 15 seconds. Then don't touch it onwards. Once it is clean, then handle it carefully. If it is not clean, it is sample which is not clean. So you can see here that there is some kind of line effects are there. This is due to the dirtiness, some kind of hydrocarbons. When we are focusing, it is leaving its impression. So this is not desirable. So to avoid this kind of artifacts, we have to clean our sample very nicely. So to remove hydrocarbon, we are supposed to clean our sample with organic solvent such as acetone or methanol, and we have to, after this cleaning, we are not supposed to charge our sample. So these are some precautions which needs to be taken care. One more precaution for non-conductive specimen, because we are talking about the secondary electron. Now what will happen? Suppose this is your sample surface. Electrons are coming. Suppose if the electron is accumulated here, so what will happen? This will not allow the incident electron beam to reach the specimen. So kind of scattering will be there. So we will get wrong information. So what we have to do, whatever electron is accumulated here, so we have to provide a path to go to we have to ground this sample. There are two ways. First, your sample should be coated nicely with some conducting layer, kind of gold or anything which is conducting. Generally carbon or gold is coated, so to avoid accumulation of charge over here. Sometimes we need to provide path also. If it is very insulating, generally we provide path with silver paste. So suppose there is some charging effect, so we will get this kind of artifact. Can you see? We can't see any kind of, we can't take any kind of information due to charging. So just because just now I mentioned, if suppose electrons are accumulated over here, electrons are coming, so it will just deflect it. We can't see any information, just bright spot. Whenever you have bright spot, it means your sample is very non-conductive and it is a charging effect. It is not feature of your sample. So you have to again prepare a sample. How we can prepare? You have to coat your sample with some conducting material, and then you should provide a conducting path as well. So these are few suggestions for the sample preparation in the SEM machine. Now let's come to the transmission electron microscope. Transmission electron microscopy is very much similar to the optical microscopy. What was the need? In the earlier also I mentioned, first depending upon the feature size, you are supposed to select your instrument. Suppose if you can see some features through the optical microscope, then you should not go for scanning electron microscope. If your features are less than 150 micron, then only you should go for the scanning electron microscope. Suppose your features are less than 10 nanometer, then only you should go for transmission electron microscope. So what is in SCM is very good. Minimal sample preparation, and we can get 3D information as well as compositional information. TM is a good technique, but it requires lot of sample preparation. It is again used for topographical study as well as for crystal structure study. Let's say, so utility is in the microstructural study as well as the crystal structure study. This is the first picture of the transmission electron microscope. This was demonstrated by Knoll and Ruska in 1931. This is the first commercial TM 1939. Later on, Ruska got Nobel Prize in Physics in 1986 for this construction of the machine. So these are the picture of some modern TM machines which is available nowadays in the market. So as I mentioned, there are different kind of interaction of electrons with matter, elastic scattering and elastic scattering. The important for the TM and analytic TM and TM is elastic scattering. So electron which is suffering from the change of velocity, that is energy, is used in analytical TM, means conventional TM. However, for HRTM, there are different kind of electrons are there in the TM machine, elastically and elastically. Elastically used for the conventional TM and elastically scattered for electron for the HRTM. We will come what is the HRTM. This is a bright field image, dark field image. So let's come to the instrumentation part. As it was in the SCM machine, there is an electron source, and then there is a illumination part, and then sample stage imaging, and then magnification, then data recording part. So depending upon the acceleration voltage, wavelength of electron wave can be controlled, and hence resolution can be controlled. In a typical TM machine, generally up to 200 kV is applied. However, in higher end, it can vary from 40 to 500 kV. The best possible resolution with the TM machine is 0.2 nanometer, and resolution up to 10 to the power 6 can be achieved. So this is again summary of the signals from the for the SCM and TM machine. So in the conventional TM machine, there are different kind of signal like inelastic scatter, elastic scatter, and different kind of undivided beam. And this all we have seen in the SCM. That is a elastically scattered electron. That is inelastically scattered electron. Then X-rays for composition analysis. Different kind of signals are used for different purposes. Similarly, for the TM also, different kind of signals are used for different purposes. Like inelastically scattering used for the conventional TM, and elastically scattered used for the high resolution TM images. We will come across. So this is a sample preparation as mentioned as tedious task for this TM machine. So this is a sample holder. This very small piece is shown over here, and then here is your TM grid. This is again this is a zoom view of this portion, and this is zoom view of TM grid. This is generally of copper. These are the some mesh, copper mesh. So generally what we do, suppose your sample is in a powder form, we dissolve, kind of disperse in some solvent which can evaporate like DI water or acetone. Then we keep it in some ultrasonic cleaner, and then we put few drop over here, so that some particle of your sample can come over your TM grid. But make sure this sample are electron transparent. Electron transparent means less than 100 nanometer. This is very important criteria for the TM machine. Your sample should be electron transparent. That's why all sample cannot be analyzed in your TM machine. Your sample should be electron transparent. This is very important. Now thinning of the sample. This is must. Suppose you have sample which is not electron transparent, so we have to make it electron transparent. Let's assume this is your sample which is having some 3 mm thickness. Okay, suppose if you want to take out sample from here, so we have to go for pre-thinning. Means pre-thinning, polishing or something you have to take, and then you have to thin it down, let's say 0.1 mm. Then for final thinning you can go for electrolytic thinning or ion milling. This is generally done for the focused ion beam. So gallium ion is kind of directed towards this region. They take out the material from here. So this area gets very thin, that is electron transparent zone. This area becomes electron transparent zone. We cut it and we take it to the electron grid, TM grid. So there again, like in the SEM, we did image formation. So there are different kind of contrast. So contrast means again number of electron, play of the electron. So there should be sufficient contrast in image. So here in TM, your contrast relies on the deflection of electron from their primary path. So, there's, let's say, suppose this is your primary path, how much they are deflected from their primary path, this will decide your contrast. This contrast is basically generated due to a difference in the number of electrons scattered. This is a transmitted wave. How many of electrons are scattered from the primary path, or how many going in other direction. This will decide the contrast in the TM machine. Again, there is a two mechanism. We will see one by one. First one is mass density contrast. So deflection of electron from the whatever is there electron in your, suppose you are having some sample, some atom is there. So deflection of electron from the electron of atomic nucleus, they will what will produce? They will produce collision with the electron. Incident electron will collide with your atom inside your sample. So after this interaction, the electron will change its path after collision. Okay, so this is known as a mass density contrast. This is generally used for the non-crystalline material, which is not polycrystalline sample or single crystal. So this is mostly used for the amorphous sample. How we define contrast over? Contrast is defined as a C is equal to I0 minus IT over I naught. So what is I naught? The incident beam intensity is I naught, and the transmitted beam intensity, this one is IT, transmitted, T for time transmitted, and D for, so this ratio is known as a contrast formation. So this is for the amorphous sample. So basically mass density is defined as a product of density and thickness at this point. Let's say suppose if you want to take image over here. So this is defined as density of the material and thickness over here. So this is main mechanism for the formation of the TM image in amorphous solids. Now let's come to the optical path. So this is your optic axis, this is your objective lens, this is object plane, and this is your image plane. There is one very important plane, that is back focal plane, diffraction plane. This is the plane from where we can get information about the structural information about the material. It is used for the structural analysis. Let's come to the diffraction contrast. So first one was mass density, that is what for the amorphous. This is for the polycrystalline material. So here what is the diffraction? Diffraction is basically collective. If you can see, this is a sample, this is an incident beam, that is I naught, and all are collectively deflected. Collective deflection of electron is known as a diffraction. So again, diffraction contrast is a main mechanism for image formation in crystalline specimen. So basically here electron, if you can see, they scatter collaboratively by see, if you see here, these are parallel plane of atoms, which is there in the polycrystalline material, not in amorphous. That's why diffraction contrast we get in polycrystalline material. So electron is scattered collaboratively by crystal parallel plane. So this is Bragg condition. We know it from the XRD also. Whenever we get peak in XRD diffraction pattern, so Bragg condition should satisfy. Similarly here also, if we suppose this Bragg condition is satisfied at certain angles, so we get constructive diffraction pattern. So here the electrons are coming, and here is a sample. So this is enlarged view. So at some condition, if suppose this Bragg condition is satisfied, what we will get? We will get constructive diffraction pattern. So corresponding to constructive diffraction, we will get this kind of spot, and the spot is in back focal plane. This is known as a back focal plane. This is your back focal plane. Now this is again optic path of TM machine. So in TM there can be images can be taken in two modes. First one is image mode, Second one is in diffraction mode. Suppose if you want to take image mode, so what this is for the image mode. So this is your optical path for the image mode. So there is a specimen, you have kept your specimen, then objective lens, reciprocal space. This is, and then you have your image is forming over here. Then you focus, kind of project your image over here. This is focused on the image plane over here. However, in the diffraction mode, what is there? This is your polycrystalline sample. Some beams are being deflected over here. As I mentioned, some dots are being formed. You see, some dots are being formed back focal plane. So in diffraction mode, whatever is formed on the back focal plane, that is kind of projected on fluorescent screen. However, in the image, whatever is formed on the image plane, that is focused on the fluorescent screen. That is the difference. The image plane is projected on the fluorescent screen in the image mode. However, in the diffraction mode, back focal plane is projected on the fluorescent screen. So this kind of dotted pattern we get. So we will see. So this is basically diffraction mode. Can you see this spotted pattern? So suppose your sample is crystalline in some area. So just we focus, select that area, and we get this kind of selected area diffraction pattern. From here we can get lot many information about the structure of the structural information, like lattice parameter, lattice spacing, d-spacing, lot many. Even phase formation can be, even suppose you have some defects in crystal, that can be estimated from the this diffraction pattern. So this kind of pattern can be obtained if we focus back focal plane over fluorescent screen. Now in this also there is two kind of images, bright field and dark field. As I mentioned that for this kind of images we use elastically scattered electron. For conventional imaging we use inelastically scattered conventional TM, and for dark field and HRTM, high resolution TM, we use elastically scattered. Again there are two modes, bright field and dark field. What is bright field? Suppose these are your back focal points. So, suppose if your light going transmitted way to pass with the objective aperture. This is our objective aperture. If we allow this transmitted beam to pass through, this is your this is your central spot. If we allow to pass through, this is your bright field. And if we stop, somehow it is, if you see this is stop, we just allow to diffractive beam to pass through. This kind of image is known as a dark field image. So this kind of image, that is dark field, is obtained by not allowing the diffraction and this transmitted beam to the objective aperture. However, bright field image, we allow the transmitted field image to pass through the objective aperture. So this is the main imaging mode in TM machine, bright field and dark field. In bright, transmitted beam is allowed to pass to the objective, and in the dark field image, only diffracted beam is allowed to the pass to the objective aperture. So in this way, we can get lot of information with a combination of both, the bright field as well as dark field. So this is some example of bright field images of aluminum alloy. So here again the contrast between A and B can be seen. So here whatever is, see here it is bright, but the same is dark over here. So this is the difference. Why this difference is there? Suppose the same sample is here. We have just tilted the sample. This is the effect of tilting of the sample in the TM machine. Once we have tilted the sample, Bragg condition is disturbed. So whatever was being satisfied, that is not satisfied, that is satisfying in some other area. Earlier this was satisfying for this, now it has changed for something else. It is completely destructive for this. So this individual grains can be marked with numbers just by tilting of the specimen by few degree, maybe less than 1 degree even. So just by tilting of the specimen, different kind of images can be obtained. Entire kind of structural analysis can be performed. Now let's come to the phase contrast. We have seen mass density contrast as well as diffraction contrast. Mass density is used mostly for the amorphous solid, and diffraction contrast for polycrystalline sample. In both the contrasts, generally we use electron waves, phase difference in the electron waves. But in HRTM, that is the elastically scattered electron beam passing through the sample, we use its phase. So it gives additional information, better resolution. That is why it is known as a high resolution transmission electron microscope. Because in a mass density and diffraction contrast, we are using amplitude contrast. But in HRTM, we are using phase contrast. We are using phase of the electron. See, just now I mentioned that electron is associated with the wave. So this wave is having amplitude as well as phase. If we are using amplitude only, so it will give either mass density contrast or diffraction contrast. But if we are analyzing its phase also, so it will give us high resolution TM images. These images, the same machine, but its resolution will be improved. So phase contrast should involve at least 2 electron beams. And what are that electron beam? That one should be transmitted and one diffracted beam. Means it should be bright field only. It can't be dark field. Because in dark field, if you remember, just now I told that transmitted beam is blocked through the it cannot pass through the aperture. So for HRTM image, it should be the bright one, bright field imaging. At least you have the transmitted beam, then only with respect to that you can see the changes in the phase of the diffracted beam. This is a very important point. The phase change in the diffracted beam should be measured with respect to transmitted beam. So two beam, there is must to take two beam. That is a bright field. So it is must to involve at least 2 electron waves that are different in wave phase. If it is being diffracted, then definitely its phase will change, and it will have information about from where it is being diffracted, from which crystal plane it is being diffracted. Okay, so a crystal structure with periodic lattice like this kind of structure, if it is being diffracted, or this kind of structure, different structures there, this will have information about whether it is being diffracted with D-spacing something, let's say D1 or let's say D2. So it will have this information. So this will be used for the HRTM analysis. It will form kind of fringes. I'll come to this. So can you see these fringes? This is HRTM images. So these fringes are used for the HRTM analysis. This is constituted from the phase contrast. And again here you can see some bright image, some dark image. This is a jet contrast. This is basically silicon germanium alloy nanowire. This I have given from my PhD thesis. So there I have synthesized silicon germanium alloy nanowire. So in fact TM analysis confirm uniform distribution of germanium in silicon. Here you can see some dark images because germanium is having germanium is higher than silicon. So whatever is brighter place, that is confirming the presence of germanium, and other is silicon. So germanium is uniformly distributed in silicon. Again this side pattern is confirming ring pattern. If it is polycrystalline material, then it will be ring pattern. If it is amorphous, then it will be diffuse ring. This ring pattern also can give us lot of information. If it is kind of amorphous diffuse ring, so it is amorphous, but here you can see it's spotted, it means it is polycrystalline. Now from the place separation, from where it is coming from the phase contrast in the HRTM. This phase is coming from the from the fringes we can measure the interplanar spacing. Here you can see 0.55 nanometer. So this is basically this lattice spacing, that is lattice constant of the silicon germanium. So this was all. Here I have, for detailed data analysis, I have provided a link, very interesting link. The main thing is data acquisition is okay, but data analysis is as important as data acquisition. Data, three things. First thing is sample preparation, second one is data acquisition, third is data analysis. So since due to limited time, I am not able to discuss data analysis, but you can watch this video. Link is given over here. So it's very interesting. So this was all about the TM analysis. These are a few references which I have considered for making this notes presentation. So this was was all, and thank you all for your kind attention. Thank you.